Since its creation, the Earth has never stopped changing. Colossal forces have hurled ocean floors upwards and made them into towering mountain ranges. Incredible collisions have created entire continents. These tectonic forces are still at work today. We see them in volcanic eruptions, earthquakes, and tsunamis. Tectonics sculpt our landscapes, change our climates, dry up our oceans, and can destroy life. Europe was created by 3 collisions, with America, with Asia, and with Africa. But even if Europe has taken solid form, it hasn't stopped changing. The tectonic plates that have squeezed Europe from all sides are still pushing, tearing, and knocking against each other. These movements are altering the very shape of the continent, causing overwhelming and often destructive events. Tectonic forces have built majestic underground formations, as well as bringing the devastation of major earthquakes. And they may yet erase the Mediterranean from the map. These are only a few of the consequences in the tectonic confrontation of the voyage of the continents. The continents of Europe and North America started to separate 180 million years ago, creating the Atlantic Ocean. But the edges of the tectonic plates on which these continents lie are still very close to one another. Straddling this meeting point is the volcanic island of Iceland. Iceland is literally split by the fault that divides Europe and North America. The Earth's core releases its heat at this boundary. There are boiling mud pots, geysers, and crevasses that are literally tearing Iceland apart. If you dive into this unstable fault, you can actually touch Europe and North America at the same time. At this point, the 2 continents are moving apart at a rate of 2 centimeters a year. But southern Europe, around the Mediterranean, is the scene of the most recent construction project in Europe's geological history. 65 million years ago, the collision between Africa and Europe displaces billions of tons of rock and raises them thousands of meters above sea level. This became the Alps. They tower over the European continent, reaching an altitude of more than 4,800 meters. It's the perfect landscape for crystal hunters, an intrepid breed of adventurers who risk their lives searching for these beautiful geological treasures. Jean-Frank Charlet has lost several friends and family members to the perils of crystal hunting.
In my family, we've been guides and crystal hunters for generations. I grew up seeing the men collecting crystals, and I guess I caught the bug. Every day in summertime, 2,000 or 3,000 climbers come to the Chamonix Valley, but no one really finds crystals. Someone knowledgeable has to take you to the right place and show you how to go about it. The veins of quartz are usually high up in the mountains. You can spot the holes in the cliff face from a distance. We select one and either take an easy route up, then rappel down to the cavity, or climb straight up to it. And of course, crystals are found in places where the rock is very porous and highly fractured. So there's always the risk of a landslide or a rockfall.
An opening a few meters higher up catches Jean-Franc's eye.
The big white ball, the hole in the middle, and the veins below.
The precious crystals that Jean-Franc and his climbing partners are searching for so intently were created in fissures that opened up when the Alps were formed.
A nice bit of climbing.
Yeah, it's an easy climb. You're going to like this. It's a good hole with crystals in it, a really good one.
A little more to the left. It'll come out.
It's all split. It's not easy. Part of it is still attached.
Look, there are more. Small, nicely shaped. Pretty. Look at that point. It's huge. Look at this. Beautiful quality.
For Michel Catalino of the University of Nantes, crystals are time machines that can take us back to the formation of the Alps. He uses lasers to recover drops of water that are millions of years old.
This crystal tells us a lot about the formation of the Alps and about the conditions that prevailed as the crystal formed. And they were extreme, 400 degrees, 3 kilobars. That is 3,000 times greater than standard atmospheric pressure. That amount of pressure indicates a depth of 12 kilometers, which means that the crystal was formed 12 kilometers underground. The reason it was found on the Mont Blanc Massif today is because the granite gradually rose up to the Earth's surface, and all the layers above it eroded away.
C'est transparent. Ça monte au cerveau, puis on se sent un peu bizarre quand même. Bravo!
Crystals are created only under extremely rare conditions. The quartz that formed this prism was pushed down towards the Earth's core when Europe and Africa collided. Under the weight of 2 continents, the particles decomposed, reassembled, compressed, and finally were lifted back up inside the Alps to form smooth, 6-sided crystals.
We always hope our packs will be bulging with crystals on the climb down. Our days are challenging and difficult, but the joy of finding these treasures makes it all worthwhile.
Once again, Jean-Franc Charlet's long experience as a crystal hunter has not only helped him find valuable crystals, but to return safe and sound from his adventure. These sparkling crystals, sculpted by immense tectonic forces, are the beautiful byproducts of the creation of Europe's highest peaks. In Provence, not far from the Alps, the rock formations of the Esterel Massif are identical to the rock faces of Corsica and Sardinia, which are hundreds of kilometers off the southern coast of France. This has long intrigued scientists. They've wondered whether these separate formations have been joined and then torn apart by tectonic forces. To uncover this past, 2 scientists are meeting on the San Pietro Peninsula in southwestern Sardinia. Jérôme Gatticheca, geophysicist and planetologist at the University of Aix-en-Provence, has come to work with Roberto Rizzo, a specialist in the geology of volcanic terrain. The 2 researchers will take a trip back in time to determine whether Provence, Corsica, and Sardinia were once part of a single landmass.
Ciao Jerome, come stai? Bene. A posto? A posto. Andiamo, con la macchina di là. Sì, andiamo.
To understand the geological history of this area, Jérôme focuses on the unique makeup of the rocks found on the San Pietro Peninsula. These cliffs are made from a lava flow that came from the Earth's interior, which then solidified as it hit the colder air and water. Jerome and Roberto see an outcrop that could help them recreate this 20-million-year-old journey from the center of the Earth.
We'll take a sample from this lower lava flow. The layer above it is from a brief period in Sardinia's history when volcanic activity stopped and the products of erosion were carried here by water. That's these rounded shapes here. Higher up, there's another lava flow, which is only about 15 million years old, one of the youngest flows on the island.
To understand the exact path taken by the rocks on this peninsula, Jerome must first determine their makeup and their age.
This geological map shows rocks here and here that are between 300 and 400 million years old, and much more recent rocks that appeared 30 million years ago. These volcanic rocks contain ferrous oxide crystals called magnetite. As the molten rock cools, the magnetite records the direction of the Earth's magnetic field.
By understanding the magnetic properties of these rocks, Jerome will be able to trace the exact route taken by Corsica and Sardinia when they separated from the south of France. So Jerome drills through the magma to find samples that contain magnetite. It is a time-consuming undertaking. Jerome has to take volcanic bore samples of different ages of rock, from different lava flows, and from different sites. He'll need hundreds of samples to do his work. Jerome carefully records the position and orientation of each bore sample. But these samples will only give up their secrets in a laboratory in Aix-en-Provence. In a metal chamber shielded from the Earth's magnetic field, Jerome uses a magnetometer to read the magnetic signature of the volcanic rocks of San Pietro. These signatures were recorded into the matter when it solidified into rock. This painstaking procedure allows him to plot the position of Corsica and Sardinia in time and space. What it reveals is that the Corsican-Sardinian block separated from the south of France 30 million years ago. The archipelago then rotated by 45 degrees and created an opening that formed the western part of the Mediterranean. The Mediterranean is full of surprises. In 1968, oil prospectors discovered salt formations more than a kilometer thick. Trying to understand what caused these startling accumulations, scientists have now brought to light an extraordinary moment in the history of the European continent. Antonio Caruso of the Geology and Geodesic Department of the University of Palermo describes what researchers call the Messinian salinity crisis.
This is the Mediterranean we know today. But 6 million years ago, it was at the heart of one of the most incredible disasters that the Earth has ever known.
The cause of the disaster? The collision of Africa with Europe, a tectonic event that separates the Atlantic from the Mediterranean.
The uplifting of the sea floor blocked off the Mediterranean, and it became landlocked. Without the water from the Atlantic flowing in to fill it up, the Mediterranean began to evaporate. The Mediterranean basin dried up and became a Dead Sea. Once that happened, the organisms living in Africa were able to cross what was now a salt desert and migrate to Europe.
The Messinian crisis killed all the marine animals of the Mediterranean.
Around 5.3 million years ago, another tectonic upheaval reopened the channel between the Mediterranean and the Atlantic, allowing the water to flow freely in and out again through what we now call the Strait of Gibraltar. Towering waterfalls formed, and in a very short time, perhaps less than 500 years, the marine species living in the Atlantic recolonized the Mediterranean.
The refilling of the Mediterranean Sea was both rapid and violent. Some researchers think that it took a mere 11 years. 11 years to fill an entire sea 2,000 meters deep. All that water gushing into the Mediterranean caused the world's ocean levels to drop by about 15 meters. But as the Mediterranean dried up, the salt it contained was left behind on the seabed in deposits of up to 1,500 meters thick. At Real Monte in southwestern Sicily, the drying of the sea formed a wall of salt as breathtakingly beautiful as a stained glass window.
We're now in the most spectacular part of the Real Monte mine. This looks like a work of art, a giant mural painted by a genius, but it's a natural formation. This magnificent wall of concentric circles is made entirely of salt. It's a series of alternating layers of salt mixed with different types of clay in varying proportions. The layers are about 30 centimeters thick, which were then compressed by the tectonic activity unique to Sicily. These sedimentary deposits were formed at a depth of 1,000 meters. But the convergence of the African and European plates lifted everything up so that it is now only 60 meters below the surface.
Fino ad arrivare a circa 60 metri di profondità sotto il livello del mare.
The Real Monte salt mine shows how extraordinarily powerful and diverse tectonic forces are. They can wipe out life, but they can also create natural masterpieces. Of course, it's not only tectonics that transform the Earth. In Postojna in southern Slovenia is an example of the power of erosion, a force that has changed the contours of a large part of Europe. The word karst, which comes from Slovenian, describes a limestone formation that has been worn down and reshaped by water. 1/5 of the Earth's surface has been shaped this way. Water erosion creates strangely twisted landscapes, digs underground rivers, and creates awe-inspiring caves. The limestone in this cave was made from the shells and skeletons of microorganisms that accumulated over millions of years at the bottom of a now-vanished sea. Later, the limestone was hollowed out, creating a gigantic network of caves and underground galleries. Nobody knows exactly how far this labyrinth goes. Day after day, raindrops penetrate the Postojna cave and continue to shape and polish the surface. Andrej Mahevich works at the Karst Research Institute in Postojna.
We are something like 60 meters below the karst surface in an old passage that was created by a former river. The river moved now to a lower passages, but here it is dry, not completely dry, because through the ceiling there are droplets of the water coming. It's a rainwater which fell on the surface, found its way to the small little cracks where it dissolved some limestone, and each droplet deposits a little bit of calcium carbonate and forming, so in thousands of years, these stalagmites, which are slightly growing and filling the empty space.
The Postojna cave was made from materials that came from the sea. It was hollowed out by a river. But it all started with the shift of tectonic plates.
At the end of the Eocene period, about 30 million years ago, because of the movements of the big African plate towards Europe, all this area was uplifted from the bottom of the ancient sea, and the limestones were exposed to the act of the rain. And at that time, the karst erosion started. It is a slow dissolution of limestone, but at the end, a huge landforms were created, and among those landforms, the caves are the most magnificent. And the result of this long evolution is what we have today here, a big 20 kilometers long Postojna cave.
Caves are an invaluable source of scientific information. They can reveal how the continents were formed and how climate has changed over vast periods of time. And they can tell us about who lived nearby or inside. The Gargas Cave in the Hautes-Pyrénées region of southern France has traces of the earliest human beings in Europe. This is the beginning of our modern species, living on an Earth that must have seemed all-powerful. Jean Clot, a historian of this period, believes that humans have always had a deep relationship with the natural world around them.
Stone Age humans did not dominate nature, nor did they try to. They saw themselves as being part of nature, just as the animals were. But that didn't stop them from trying to draw on supernatural forces, especially by going into caves. Cave paintings were certainly done for this purpose.
The first human beings to enter Gargas covered the cave walls with outlines of their hands, a spiritual act according to Clot.
The hands are a good example. Here at Gargas, we found about 220 hand imprints from men, women, and children. In this case, there's a clear intention of contacting supernatural forces.
At the time that Homo sapiens left these traces on the walls of the Gargas cave, the Earth was emerging from an ice age that had lasted more than 100,000 years. Norway's Svalbard archipelago seems to still be in the ice age. Glaciers have carved the solid ground into mountains, valleys, and fjords. Although it's larger than many countries, at any given time, Svalbard's population numbers barely more than 2,000, many of them scientists studying the Earth in these extreme conditions. From their point of view, Svalbard is a fascinating frozen laboratory. Astrid Leisa and Eliv Larsen work for Norway's Geological Services. They explore the length and breadth of the archipelago, trying to understand the history and the future of Europe's glaciers.
About 60% of the Svalbard is covered by glaciers. What I find very fascinating with glaciers are how they form the landscapes. The last millions of years there have been many glaciations in the northern hemisphere, and every time the glaciers have started to build up, it moves out to the coast, to the shelf, and it erode deep into the valleys, into the fjords.
Standing here, it seems like it's not moving at all because we're standing on solid ice, and it seems to be totally stable. But some glacier moves at incredible speed. The normal speed for glacier would be a few meters a year or something like that. But they can move like 5, 6, 7, 8 meters a day for maybe a year, and then they actually advances at that speed, and the front can move kilometers in a year, and then they go on for another quiescence phase, building up this moving capacity. So they go through these cycles, and many of the glaciers in Svalbard do that.
Eliv and Astrid are heading into Van Mayen Fjorden. It's an 83-kilometer valley dug out over thousands of years by the Paula Glacier. By studying the fjord's past, geologists hope to discover how the glaciers changed the European continent during the Great Ice Ages, which began more than 2 billion years ago. Over that time, glaciers have deposited grains of sand on the frozen lands of Svalbard. These particles formed mud beds which are only accessible by hovercraft. Each of these particles holds the history of the glaciers that forged this landscape.
What we're doing here is that we take surface samples of these tidal sediments. So we are now at low tide and most distal position relative to the sediment source where we can sample.
During the last ice age, more than 10,000 years ago, ice covered much of Europe. London, Paris, Berlin, Vienna, all buried under tons of ice. The deposits of mud and sludge left by glaciers in France and Germany would have been quite similar to what Elive and Astrid are examining today. Near the mouth of the fjord, Elive and Astrid are struck by a geological feature that may have been formed by the movement of the Paula Glacier that eroded the valley. This glacier is moving so rapidly that Elive and Astrid barely recognize the physical features that they saw just 6 months ago.
From here anyway, so. Oh, there's the sea behind there, right? Okay. Oh, also look here, it's a fantastic view of the ice front here. It's even better than I thought. Ah, these days just make it all worth it, you know, it's fantastic.
But what is perhaps even more interesting is that the glaciers caused a vertical tectonic movement in Europe. When they melted, the absence of their enormous weight literally lifted the surface of the Earth dozens of centimeters. Glaciers act in ways quite like tectonic plates. By observing them, scientists can learn more about what happens when plates collide.
What we can see here is a nice little example of a glacial tectonics, which is actually the effect of the glacier moving over sediments and deforming them. So this is actually in miniature what's happening when a mountain chain is formed.
For hundreds of thousands of years, glaciers have wrinkled and folded the rock along their path, in much the same way as tectonic forces created the Alps. The 17-kilometer-long Paula Glacier scoured out this valley like a giant drill. And like a massive bulldozer, it pushed billions of tons of stones in front of it. In only a few years, just a blink of an eye in geological time, Paula created rock formations that astonish Elive and Astrid.
Basically, you see the same kind of sediments here as you see on the present fluvial plain down there. You have the coarse-grained gravel, as you find in the deepest channel out there, and then you have the fine-grained sediments.
I'm really glad that we still have the glacier there, because if I came to this spot and didn't have the glacier there, I would probably never have thought of that this is belonging to an end moraine, because this is fluvial sediments that actually belong to a much lower level.
One day, Elive and Astrid's research should allow them to predict the behavior of the glaciers that are still reshaping northern Europe. 4,000 kilometers south of Svalbard, the African plate is plowing into Europe. And in Sicily, you can still see how it's transforming the landscape. This tectonic collision created a volcano whose peak towers 3,000 meters over the city of Catania and its 300,000 inhabitants. At Catania's National Institute of Geophysics and Volcanology, scientists are trying to predict the behavior of Etna, one of the world's most active volcanoes, using cutting-edge technology. Etna is covered with a vast array of sensors to capture an immense quantity of data. They monitor earthquakes, tectonic plate movements, and the changing chemical composition of the volcanic flow. All of this information is relayed to the observation center in Catania. The geologists can even watch the boiling lava live on screen. Although some researchers, like volcanologist Salvatore Giamanco, prefer to observe Etna with their own eyes.
Etna is a perfect natural laboratory for volcanologists. Etna has many different types of eruptions, and for example, during the last 30 years, we have witnessed almost any kind of eruption known on active volcanoes on the Earth. So going from mild lava flows to lava fountains, even to pyroclastic flows, which is something unusual for Etna, but it happened.
The exceptional variety of eruptions comes from the complex nature of the volcano itself. Etna has 4 mouths and more than 300 erupting vents on its slopes. The maze of the volcano's inner plumbing is continually changing, making Etna unstable and unpredictable.
So here, I think that it will very gradually get bigger and eventually form a sizable crater.
Etna is a special case. It's located right on the border of the African plate to the south and the Eurasian plate to the north.
Africa pushes into Europe, cracking northern Sicily in several places, tearing the crust into microplates. Eruptions spew from these gashes. Other lava flows come from the movement of one tectonic plate over the other, allowing lava to surge onto the Earth's surface. This can be seen in both Etna's craters and its vents.
This vent represents the first sign of activity at Mount Etna after the end of the last eruption. It's very important for us because it's a way to monitor the evolution of volcanic activity at Mount Etna. And also, this vent is important because it formed at the crossing of 2 of the major tectonic lines of Etna. And as you know, tectonics rules the way Etna evolves. So having a new vent that opened in a new location, which has never been used by a crater before, it means that something new is happening tectonically on Mount Etna.
The jostling of the African and European plates keeps changing Mount Etna. Even its altitude changes when lava erupts, and every tectonic movement alters the position of the vents and craters. Whenever this happens, geologists have to readjust their sensors.
Volcanoes are probably the best example of a living Earth. So our planet is full of energy. In the last years, we tried to develop techniques that do not force us to be so close to the eruptive vents. I'm talking about remote sensing techniques. The use of satellites, for example, is the future, actually the present of our job. But we still want to be close to the volcano. It's something so strong because I strongly believe that by looking with naked eyes to such a phenomenon, you get more information than simply looking at a monitor with data taken from thousands of kilometers above the volcano. There are indicators that something is changing on the volcano, even months before the onset of the eruption. Mount Etna can be dangerous mostly for the properties. Lava flows destroy everything during their path, but unfortunately, lava flows are slow enough to let people leave their homes and sometimes even take all the furniture from their house. So the problems are relatively limited compared to other volcanoes in the world.
The largest eruption of Mount Etna in modern times took place in 1669. Lava flowed for 4 months, destroying half the city of Catania. And no amount of modern technology could prevent such a disaster from reoccurring today. The impact of the African plate did more than create volcanoes. Its thrust cracked the crust all around the Mediterranean. The collision of these smaller plates could produce earthquakes and tsunamis at any moment. One tectonic fault split Greece in two. The space created between the Peloponnesus and continental Europe is called the Gulf of Corinth, one of the least stable spots on the planet.
Dans 5 minutes, dans 6 heures, donc ça va, 22 heures, ça serait parfait.
Pascal Bernard and Anne Deschamps are doing more than just studying the tectonic forces battling each other in the Gulf of Corinth. Their mission is to establish an observation system to warn the population of a coming earthquake. Half of Europe's earthquakes occur in Greece, and the western part of the Gulf of Corinth is particularly vulnerable. In 1995, in the Aggio region, an earthquake measuring 6.1 on the Richter scale killed dozens of people. This is where Anne and Pascal are concentrating their efforts. They want to establish a comprehensive network of sensors to capture the earth tremors and plate movements that cause tsunamis.
Dès qu'on a un petit séisme,
the moment a small earthquake occurs, 5 or 10 kilometers below the seafloor, a fault opens and emits seismic waves that shoot up to the surface, particularly to the top of this hill. We have set up a seismometer to record them, and the information is stored on a computer.
Pascal and Anne's team ranges up and down the shoreline of the Gulf of Corinth. They negotiate with farmers, families, even religious congregations to get permission to install GPSs and seismic devices. These would warn people of imminent danger.
Oh, maybe the switch for the power now.
At first glance, the Gulf of Corinth seems stable, but under the layers of earth, the rock bed is constantly moving.
The mountains of mainland Europe are there, and this is the Gulf of Corinth. To the south are the mountains of the Peloponnese, which are steadily moving away from the mainland by 1.5 centimeters per year. Over the 20 years I've been working here, the Gulf of Corinth has widened by 30 centimeters. Deep down, 10 kilometers below this island, the stretching causes lots of mini earthquakes, all detected by our seismological network. We think all this will generate 1 or more major earthquakes in the next 10, 20, or 30 years.
As they prepare for the next cataclysm, Pascal and Anne beef up their network of sensors. The more seismic movements they can detect, the more they can help those who live in the region. Pascal has made an interesting discovery. The Gulf of Corinth's rift doesn't just move horizontally, it also moves vertically.
Here we can see the rift. There's one block on one side of the rift, and we're standing on the other block. The contact between the two blocks can be seen in this striated plain that continues down into the earth for 5 to 10 kilometers. Underground, it intersects the Aegean fault below the town. Both faults are moving northward and they join up. That's where all the minor earthquakes happen, about 10 kilometers from here. So the rift lifted this block up about 600 meters. It runs 20 kilometers this way and 15 kilometers that way. And after 100 earthquakes, it has created a small mountain.
The population of the town of Aigio is about 30,000. Pascal Bernard believes that the next major earthquake in the Gulf of Corinth could fundamentally change the shape of the town.
On the left, the buildings of the town are all along the upper part of the Aegean Fault. Here, we're on the lower or north side of the fault. When the next earthquake occurs, the upper part will rise. This part of the port will drop 1 or 2 meters, and the sea will drop along with it as the block of crust moves. And if the earthquake causes major seafloor slippage, so much water will pull away that it'll rush back in a large tsunami, as happened 150 years ago when 6-meter-high waves crashed onto the port of Aegion. All the houses at sea level will be swept away.
The system of faults that threatens the small city of Aigio stretches over 1,600 kilometers. These cracks in the Earth's crust go all the way to Turkey, where they end less than 30 kilometers from the city of Istanbul. From its days as the capital of the Roman and Ottoman empires, Istanbul has been one of the world's largest and most vibrant cities. Soon, however, the fate of its citizens could be determined by tectonic forces that are at the city's gates. Istanbul is only a few feet from the Sea of Marmara, a stretch of water that lies over one of the planet's most destructive and dangerous faults. Louis Gély is a geophysicist and seismologist at the French Research Institute for the Exploration of the Sea. Today, Louis is on his way to join the research vessel Urania, chartered by the Marine Science Institute of Bologna. On the Sea of Marmara, an international team of Turkish, French, and Italian researchers is working to understand the action of the North Anatolian Fault. This gigantic crack is part of a system of faults that crisscrosses all of Turkey. The North Anatolian Fault has been the epicenter of many earthquakes, including a devastating one near Istanbul in 1999. More than 17,000 people lost their lives in that catastrophe.
Istanbul is very likely to sustain a major earthquake within the next 30 years, so there's considerable danger. The earthquake is expected to have a magnitude of between 7.2 and 7.4. 15 million people live in and around Istanbul. Few buildings in the city were designed to be earthquake resistant, so the damage will be colossal. All the buildings erected before 1999 are at risk of collapse.
The team is conducting a study that could be vital for Istanbul. They are trying to set up a unique system that could, one day, give millions of residents an early warning in the case of an earthquake.
Events of this magnitude, the sudden release of energy of a major earthquake, have no discernible early warning signs. We are trying to determine what to observe and where and how to observe it in order to give us a fighting chance at prediction. Here in the Sea of Marmara, we're exploring the measurement of gas bubbles. We know there are gases in the middle of the fault, and we think that as the strain of deformation gets close to the breaking point, more gases will be released.
For centuries, humans have tried to predict earthquakes. Scientists have studied water movements, magnetic fields, even animal behavior, without coming up with a definitive method. Today, however, the team is relying on a new research assistant, the Bubbles Observatory Module, nicknamed Bob. Its job is to detect gas bubbles coming from underwater faults.
We're preparing to install underwater observatories that will measure the properties of the fluids and watch the activity of the bubbles released from this fault.
Bob's observations go directly to the researchers on board. The data show that they are very near the North Anatolian Fault. Once Bob has confirmed the presence of the gases, Louis Gély asks the captain to position the vessel above the fault. However, the Sea of Marmara is one of the world's most crowded waterways, and lots of different obstacles must be overcome.
We want to take a core sample from a very specific place. We know we'll get results if we can do that. Unfortunately, an important cable runs directly over the ideal spot, so that's a restriction. Now the captain has agreed to anchor 0.8 of a mile from the cable.
This is 0.76.
Okay, it's good. Let's
0.7.
No, okay, 0.76.
If we put the corer on a cable, you will have all the internet in Asia disappear immediately. If this is a communication cable.
Yes.
If this is a power cable, all Istanbul will go to a full blackout. That means that we have to put yourself on the corer and go down to take your sample by hand.
I realize the captain has his obligations, but obviously we'd like him to get as close as possible. We can't push the people who are responsible for security too hard. We have to be reasonable. So it's a nuisance, but I have to live with it.
Some people find the research work an inconvenience, even if it's designed to save lives. Finally, everyone agrees on a new sampling site. The team moves into high gear, and soon the ship's captain drops anchor above the fault.
Fondo, fila 20 metri ancora. Fondo laboratorio.
To capture gases emerging from under the Earth's crust, the technicians have a huge drill that collects samples from right inside the fault.
In the 20th century, the entire Anatolian Fault moved, except for the Istanbul area, which has ruptured in the past. According to archival records, there was a major quake in 1509 and again in 1766. The rate of recurrence of earthquakes along the fault line is approximately 250 years. So we're due.
Technicians and scientists work as fast as they can, removing a bore sample from the fault. They want to see if the sample contains gas hydrates such as methane, which come from deep inside the Earth. A preliminary analysis can be done right on the ship. The sample is labeled, then the gases are extracted. The research team has guessed right. The sample does contain gas hydrates. If their theory is correct, this gas bubbling up from the depths of the Earth could save the lives of millions. But Louis is far from declaring victory. The research team has to take samples along the entire Anatolian Fault and establish dozens of underwater observation stations to analyze the gases in real time.
We don't expect to predict the next major earthquake. We're hoping for the one after that. I'm not convinced that the instruments we're setting up now will allow us to predict the next one.
Louis Gély knows that tectonic events are unpredictable, but he hopes eventually to truly understand the Anatolian Fault. So many lives depend on it. The Earth's raw energy, a power so great that it can move vast tectonic plates, is continually changing the face of Europe. In the northwest of the continent, North America and Europe are moving away from each other at a rate of 2 centimeters a year, creating a gaping fault that has energized the volcanoes of Iceland. In the south, the slow-motion collision between Europe and Africa continues, lifting the Alps higher and higher, causing earthquakes, and slowly but surely, bringing about the disappearance of the Mediterranean. Pitted against the phenomenal power of tectonics, Europe will never be the same again.